The last particles that we now need to deal with are the gauge bosons. You'll notice from those dot points that we don't actually have to deal with the scalar bosons, or the one scalar boson being the Higgs boson. So I won't go into that in any detail, but we can't really talk about gauge bosons without also talking about fundamental forces. The two very much go hand in hand. If you look at that list of fundamental forces in the second last dot point, you'll notice that there are 3 of them listed there, but there are actually 4 fundamental forces in our current theories of matter and how they interact. So, as I said, current theories identify 4 fundamental forces. We will have a look at all 4, mainly because the 4th one is one that you're familiar with, but ultimately you don't need to worry about that 4th. It's one that you'll recognise as soon as we start talking about it. The other thing that you can see from the second last dot point is that the gauge bosons mediate those forces. So the 4 gauge bosons that we've already identified and that we'll summarise here again, they mediate 3 of those 4 forces. There is a hypothesized boson that has been proposed as mediating the 4th, but it is as yet undiscovered. But it's still proposed. It's just a matter of trying to find it, I guess, is the easiest way to think about it. So we'll have a look at the summary of these in a table. So we'll have the forces listed across the top of the table, and for each force we're going to look at its strength, its range, which particles it acts on, the bosons that mediate it, and we'll also have a look at what some of the roles are of those particular forces. Now we'll list them from weakest to strongest, and the first one is the one that you'll recognise but that you don't actually need to worry about in this topic. The second is the weak nuclear force. The third is the electromagnetic, so another one that you'll be familiar with, that we do need to explain in a little bit of detail. And the last is the strong nuclear force. Now, in terms of the strength, we're just going to look at it in terms of ratios, so how strong they are relatively speaking. And we're going to start with the strongest being the strong nuclear force, and we're going to give that a ratio of 1, so everything else will be scaled down from there. So the electromagnetic force is about 1/137th, so quite a bit weaker than the strong force. The weak nuclear force is about 10 to the power of -6, and the gravitational force is 6 by 10 to the -39 in comparison. Having said that, the gravitational force is dominant over astronomical distances, so for those really long distances the gravitational force is the one that's actually the strongest, but in comparison to the strong nuclear force it's relatively weak. The gravitational force is negligible at atomic scale, so it's extremely small. So you can see they're increasing strength as we go from gravitational through the weak nuclear to the electromagnetic and finally the strong nuclear force. In terms of the range, both the gravitational force and the electromagnetic force have an infinite range, so they don't only act over a certain distance, they extend over, as we say, astronomical distances. Now, the strong nuclear force has a range of about 10 to the -15 metres. To put that into context, 10 to the -15 metres is sort of around about the diameter of a nucleus. The weak nuclear force has a range of about 10 to the -18 metres, so about 1,000th of the diameter of a proton. So very short range force and relatively weak compared to the strong nuclear force. Now the particles that are acted on by each of these forces, the gravitational force acts on all particles. The weak nuclear force only acts on quarks and leptons. The electromagnetic force, as you might have guessed, acts on charged particles, so it has no effect on neutrinos, and the strong nuclear force acts on quarks and gluons. And so you notice here that gluons are a boson, but they're also acted on by the strong nuclear force. Notice here also the difference between the leptons. So we mentioned in the previous video that quarks were the only particles that were acted on by all four fundamental forces. Leptons aren't acted on by the strong nuclear force. So there's a key difference between the two. So looking at the bosons, the particles that mediate each of these forces, or in other words, transmit the forces between particles, the weak nuclear force is mediated by the W boson and the Z boson. But the W boson has actually got two different versions. So there's the W plus and the W minus. So that means that charge can also be involved in the interaction for weak nuclear force. And then also the Z boson. So Z with a 0 to indicate that it's a neutral boson. The electromagnetic force is mediated by photons, and the symbol that we use for photons is gamma. And the strong nuclear force is mediated by gluons, and that has the symbol of G. Now the gravitational force, I'm going to put this one in brackets, is mediated by gravitons. You might note that they don't appear in the standard model. They haven't been discovered yet. They've been theorized, but there's no evidence yet that they actually exist. Maybe we'll find some in the future. Who knows? Now the roles of each of these forces, with the gravitational force, we're going to sort of state it in all its glory. It's responsible for binding planets, stars, solar systems, and even galaxies together. So fairly important force in terms of the structure of our universe. And the reason why we're talking about binding those things together is that we're really going to look at how the forces bind things. So if we jump across to the electromagnetic, we'll come back to the weak nuclear force. The electromagnetic is responsible for binding atoms together, and also for creating electric and magnetic fields. So that then means that it's going to be involved in, say, Coulomb forces. It's going to be involved in forces that are exerted on charged particles as they move through magnetic fields. So all of that detail that we covered in topic 3.2 on electromagnetism. The strong nuclear force is responsible for binding nuclei together. And because it's involved in binding nuclei together, it's also important in the process of nuclear fusion. So they're all the forces that are dealing with binding things together. The weak nuclear force is a little bit different. It's still about a force that's sort of responsible for binding, but the way we think about it is that its main role is in radioactive decay. So with radioactive decay, we've got particles splitting apart, and so it's a little bit of a different thought process behind the weak nuclear force. So it's that force that is responsible for the decay of particles in the nucleus that release beta particles in particular. It's also involved in neutrino interactions. And also in supernovae, so the explosions of stars. So there's all the fundamental forces and the particular properties associated with them, and also the bosons that mediate those forces.